just for putting together a great conference. All right, so I'm going to tell you about quantum homotopy groups. This is joint work in progress with David Reuter. We've been talking about it for like 3 years by now, and the story keeps changing. So you might have seen the same talk, but you won't recognize it because we keep changing the narrative. So that's why it's been sort of, it's one of the reasons it's still in progress. It's like I think our narrative is finally sort of settling at a steady state, but it's gonna kind of slow. Yeah. Okay. So let me start with a sort of motivating, maybe motivating question. And the motivating question I want to start with is, if you have a sigma model, what can you reconstruct about the target space? So I'll say this more precisely in a moment. We could ask sort of how much the target space can you reconstruct from a sigma model? Names for things in case I want to refer to them later. So let me say the target space might be called X, and maybe my sigma model might be called sigma of X, sigma, and let's give myself maybe a dimension in case I need it. Maybe I'm in n+1 dimensions. And so let me just quickly remind you the type of thing. So I'm a topological field theorist, so maybe I'm going to remind you that X should be just maybe a pi finite space. And whatever the sigma model is, it's the type of thing that if you input a top manifold, this just counts the number of maps. So it's the correct count, the appropriately weighted count. You all know what this is, but it's the correctly weighted number of maps. It's just like the number of maps. That's the precision function, and then you can work out your sigma model from there. I bet most people in the room have seen sigma models in some form. If not, ask your neighbor. So this is a typical question you could ask. So the type, for instance, can you figure out, like, is X connected? Can you figure out what its homotopy groups are? Can you figure out anything at all about X? Well, the answer is you can figure out some things sometimes. Maybe you can figure out whether X is empty or not. But you can't get much. The answer, not much. And the prototypical is
the demotivating answer.
So the answer is not much. So the standard example, I mean, you can be much more sophisticated in this, but here's a typical example. So a typical example is the following. So if you take X, the X to be, say, a K, an Eilenberg-MacLane space, and look at the kind of dual Eilenberg-MacLane space. For some finite group. Look at the dual Eilenberg-MacLane space. So you take this sort of Pontryagin dual to A, and you get sort of n minus p plus some constant that I have written down in my notes but don't remember. Then the electromagnetic duality tells you the statement of EM duality for any mathematician, whoever he sees this phrase electromagnetic duality. What electromagnetic duality for a topological field theorist is it's the statement that the X sigma model is isomorphic to the Y sigma. So you can't get much. Like, these things look very different. They have completely different homotopy groups. They live in different degrees, they're different groups.
So is that a fixed n, or what?
Yeah, like I'm fixing some ambient dimension when I'm studying the complement.
And so both of these are n+1.
Yeah, these are as n+1d.
And just to clarify, your demotivating answer is not much at a fixed n or for all n?
So if I was imagining that like I was walking around and I saw on the shelf of the supermarket a 5-dimensional TFT. And I wanted to like, and the sort of the ingredients list had been sort of scratched off, and I want to figure out like what sort of whether it has any natural flavors in it or something. And so, the answer is I don't know, because like one of these is organic and the other's not.
So Theo, I don't know if it's an allowed question, but if you want your sigma model to do that, what would be its action functional?
I told you the partition function.
Can you start from like Lagrangian connection?
Yeah. The fields are maps, and the
Okay.
partition function of the Lagrangian is the Lagrangian is 0. So the exponential Lagrangian is the number 1, and it's the integral over all fields of the number 1.
Okay.
It's just counting the maps.
Okay. Please continue.
So let me change the rules. So this is so let me change the rules on you. So of course, sigma models are really awesome. And the reason why sigma models are awesome is because this formula makes sense even if M has boundary. So most topological field theories only parse on closed manifolds. Or at least if you go and like buy a topological field theory, it might only make sense on closed manifolds. And it's extra data to make a topological field theory extend the manifold. But this formula just manifestly parses on manifolds. And so the sigma model comes with a distinguished boundary condition. So let me change the question from a sigma model and its boundary condition. The distinguished boundary condition has a name, by the way. So this every sigma model.
Yeah, can I follow up?
Yeah.
Yeah, pH symmetry, so I'm assuming that the reason you wrote pi finite is because you're actually secretly counting something like homotopy classes.
No, I didn't tell you what absolute value meant.
Yeah.
So of course this is this space of maps is itself some pi finite space.
Yeah.
And of course what I really mean is the appropriately weighted count of a pi finite space. So it's a sum over components of an alternating product of sizes of homotopy groups of each component.
So it's like an Euler characteristic.
Yeah, it's an Euler characteristic. It's like the Euler characteristic of pi finite spaces. So like there's two types of spaces that have Euler characteristics. The H finite spaces have a good Euler characteristic, which is like an alternating sum of Betty numbers. And the pi finite spaces have an Euler characteristic, it's an alternating product of homotopy groups. This is pi finite and not H finite, and I want the pi finite Euler characteristic. So anyway, every sigma model has a distinguished boundary condition. It sort of comes with, when you buy it when you order it, like
Where are you doing your shopping?
I decided there's like some sigma models. So anyway, every sigma model comes with a distinguished boundary condition called called Neumann. A distinguished boundary condition. It has a name, it's called Neumann. And it's the one I told you. It's just where you take the same formula and you just read it even if M has a boundary. So it's called Neumann in terms of fields. It's just the one where you just don't put any condition at all on the field. They can just do whatever they want here. There's other boundary conditions that sigma models have. For example, if you pick a point in X, so there's sort of, this is like another aside. Where do I have room to put asides? This one didn't really want to erase, which means I have to start, whatever. So as opposed to, so another boundary condition is that any point selects another boundary condition called Dirichlet. Where you set the fields to have value at that point. And of course, there's lots of other boundary conditions. You have a sub if you have a submanifold of X, I mean, X wasn't a manifold. If you have a subspace of X, you can sort of set the fields to land in that subspace. There might be other boundary conditions that aren't of that flavor, that don't have a Lagrangian description. Yeah, so this is actually a nice subtlety. This formula parses for any manifold at all, for unoriented manifolds. And an expert will know that actually this isomorphism is not true for unoriented theories. This is an isomorphism as a framed. framed TQFTs, and they have different orientation structures. Oh, let me make an aside, since I'm on shock and somebody got talked me out of using the board, so now I can just sort of ramble and not finish my talk. The word framed TFT is a terrible one. The word oriented TFT is a terrible one, because it's not the TFT that's framed or oriented. It's the manifold that's framed or oriented. And the TFT, like a framed TFT is less data, whereas a framed manifold is more data. So calling it framed or calling it oriented or calling it unoriented, like totally gets the wrong direction of how information goes. It should not be called oriented framed, it should be called co-framed TFT. Because it's a thing that's co-framed manifests. And it should be called a co-oriented TFT if it couples to an orientation, or a co-unoriented TFT if it couples to an unorientation. What's it aside? Okay. So this is as co-framed TFTs. As I said, any point selects a Dirichlet boundary condition. If I've written my space as an Eilenberg-MacLane space, I typically, well, okay, I wrote equals. That was a sort of sloppy thing to do, but Eilenberg-MacLane spaces, if you sort of remember how they deloop each other, come with a base. And this isomorphism does not preserve these boundary conditions, rather it exchanges boundary conditions. So this isomorphism for theories with boundary takes the sigma model of X with Neumann boundary, and it exchanges it for the sigma model on Y, but with Dirichlet boundary. And it's not an isomorphism of theories with Neumann boundary sigma models. So a better question I want to ask is how much about target space can you reconstruct from a sigma model with Neumann boundary? Well, I'm going to give myself the data, like I'm going to sort of keep the washing instructions on it when I
Doesn't Neumann usually mean there's a derivative condition? But that's not what you mean. You just mean there's no value specified.
Neumann means that I do not specify the position of the field, which means I do have to specify the momentum of the field. But I'm like, everything's finite, so there's there's no local fluctuation in the field at all. So
okay.
It's simple.
Thank you.
Right. So let me tell you that the answer is okay. So let me sort of this means so the answer is going to be yes. Otherwise, I wouldn't have taken already 10 minutes of the talk to tell you this part. And so sort of the slogan that I'm going to put on. The slogan that I want to put is that in general, so maybe I should put a more general question, which is to say that in general, my sort of strategy, my goal for this project, more generally, general goal is think of any pair of a TQFT with a boundary condition as some type of quantum space, as a sigma model with quantum it's like a sigma model with Neumann boundary, just for some kind of quantum target space. This is just a totally formal thing. I mean, in the same way that like Grothendieck tells you you're supposed to think of any stack at all as if it's mapping to some classifying object of that stack. Of course, a stack is not defined in terms of some object it maps to. A stack is defined in terms of like it's a sheaf on something. And you just imagine, you formally imagine that there's some object that it is the classifying space. In the same way, I would like to say that I'm going to formally imagine that any TQFT with boundary condition, I'm going to pretend that that has some target space. And that it comes in that way. And my goal is, so like think of it this way and do homotopy. Like sort of do as much homotopy theory as I can to this type of thing. That's the overall goal of our project. So let me give some examples of what we can do. And I can tell already that I'm going to get to about half the talk that I was going to tell you. So always, I mean, I want to write down formulas that parse for any TFT with boundary condition, and I'm always going to sort of double check, do they do what I want them to do in sequence? So let me tell you the type of thing that I can reconstruct. So here's an example. I should also say, like, I want to be rather indifferent, rather agnostic about what types of TFTs. Obviously, maybe I'm going to be comfortable with co-frame TFTs. I would prefer to only have to use top dimensional information. I sort of don't don't want to have to do like higher categories for image. I'd like to sort of be a one category theorist if I can. Just work with like unextended or maybe mildly extended TFTs. Like I think I know what a two category is sometimes. I really, I don't know. That's about how high I think I can think. So that's my overall goal. And that's justified because I really just want to do things like get homotopy groups out. Homotopy groups are inherently that's sort of about getting one categorical information from some infinitely dimensional object. So, okay. I mean, this is the goal. So let me give an example of the type of thing you can do. So let's take, okay, well, I'm already going to break my rules. I'm going to go down to one dimension, sort of to one's extended theories. So suppose that I'm going to still be in n+1 dimension. So let's take on an n-1 disk with its, let me draw this on another board where I can. Well, let's take an n-1 disk with its n-2 dimensional boundary sphere and another one. So this will map under my TFT. This will become some category. This is like in codimension 2, so this goes to some category. This will go to some categories. Some category. Maybe I should give it a name. Maybe my TFT is called X or something because everything's going to be called X. And it's probably some linear category, but I don't know. I'm not very good at higher dimensional linear algebra, so I don't know what type of linear category it is. It's just, I don't really know what field I'm working over. Something like a category, like maybe this is like a linear category. It has that sort of that category number. And what I definitely know is that I know that if I take two of them, then there's an interesting Bordism from two disks to one disk. It's a sort of solid pair of pants, which is called the chaps. This is the n-1 dimensional chaps. It's the name of that Bordism. And this makes this into it makes this category into an E something monoidal category.
Sorry, are those all the same n? And are all the n-2s or n-1s?
That's really an n-1,
Is the bottom sphere?
and that's really an n-2.
So when you talked about the n+1 dimensional sigma model, that meant that the Bordisms are n+1 dimensional, right?
Yeah, my space times are n+1 dimensional.
So how does that relate to the picture that you're drawing?
This is in codimension 2. So this is a codimension. So this manifold is a codimension 2 thing, and this is an n-dimensional pair of jumps. So this Bordism is n-dimensional, so it will go to a functor between categories. So this makes this into an E n-1 monoidal category. And if at least if n is not really low, so if n is at least 4, then this is just a symmetric one. Because I really mean category. I'm sorry, Hero. This is like, I just mean category. This is if you're Hero, you write down some like infinity 1 category or something like that, and I'm gonna say, screw you, I'm gonna take its homotopy 1 category. And I will proceed from there because I'm trying to do homotopy theory. And so I get to take homotopy categories if I want to. Can't stop. So
So personal. Respect your choices, Steve. Oh, it's okay.
whereas I'm like, your choices are wrong. So this is some symmetric, probably symmetric monoidal. Maybe it's a little bit less than symmetric monoidal, but usually it's symmetric monoidal for most of the time. It's a nice symmetric monoidal category. And let's compute it in the sigma model case. So in the sigma model case, what's it in the sigma model case? In the sigma model case, this is just a solid disk. A map from here to my manifold, it's my space X, is just a point in X. So the space of fields here is just X itself. And I linearize it to a category, and the way I linearize it to a category is by looking at something like the local systems of vector bundles on X. So in the sigma model case, if my sigma model is really a sigma model, then this category is like representation. It's like functors from my sigma model to back. Which notice only sees pi1 information. There's like representations of pi1. Well, the fundamental group like of X. That's what categorizes. And now let me remind you, and what is this multiplication? Well, this multi you can just check that the pair of pants becomes the standard monoidal structure. So the this Chap's monoidal structure just becomes the standard tensor product on wrap of the fundamental group way. And it's a famous fact called, I think it's called something like Tanakian duality, that says that you can reconstruct a group weight from its category representations. And so you can reconstruct, you can reconstruct it really easily so that Tanakian duality, I don't know who to attribute this, maybe to Lean, maybe Tanaka, I don't know, like different Tanaka, sorry, tells you that you can get the fundamental group weight back, that the fundamental group weight of X is kind of spec of this category. And more generally, Tanakian duality tells you that if you have any symmetric monoidal category at all, you ought to think of it as if it comes from a group. Just like if you have any commutative ring at all, you ought to think of it as if it functions on a space. Yes?
Sure. But if X has some geometric structure, then this reduces just some algebraic thing, not related to the geometric structure.
That's right, because I mean, when I said sigma model, I meant these sort of silly pi finite things that only just count homotopy classes and totally ignore any geometric structure. So the X's are like very, very finite. Classifying spaces of finite groups, that kind of stuff.
Do you not want to keep track of the comonomial structure from the same, or just?
It'll just be the adjoint to the standard multiplication. Like this is at least in characteristic 0, this is a nice symmetric monoidal category. Like sorry, this is a nice sort of in characteristic 0, this is just some finite group weight. So in characteristic 0, this is a nice semi-simple category, and the multiplication just has a nice adjoint. Actually, the multiplication always has a nice adjoint, which comes from the fact that I'm looking at finite dimensional representations. It's the fact that this category has duals is the fact that the multiplication map has an adjoint. And it'll just be that something like that. Yeah, so what I was saying is that like every commutative ring you're supposed to think of as if its functions on a space, whether there is a space there or not, and you just formally invent a space called spec of the ring if there wasn't one already. Same way, every symmetric monoidal category, you should formally invent a thing called spec of that category, which is the thing whose representations are that category. And sometimes it really is a thing, like in this case, yes.
Do we want to make like finite assumptions, or are we okay with the thing not being like
You can like my examples are always very, very finite where I can actually like really compare. Of course, I'm trying to sort of give a slogan and give a picture. And so if you have a TFT that has less finiteness, for instance, maybe it doesn't compile on top manifolds. It's perfectly plausible you have a TFT that'll compile on a pair of chaps, but won't compile on a top manifold. And in that case, this category will be a perfectly good symmetric monoidal category that will be less finite. And then I'm telling you that, well, there might no longer be an actual space, which is the spectrum of it, because it might not be finite enough for that. But you should still formally imagine it's a space. And you should still treat it geometrically, and you should still think of it as pi1 of your sigma. So what I'm really telling you is I'm telling you that any TFT at all has a group weight attached to it, or some sort of algebraic group weight, which is called its fundamental group. At least every TFT of high enough dimension. And if it's like too low a dimension, then you call it a quantum group weight, and I don't know, you write papers about quantum group weights and stuff. So that's what, as far as I can tell, what every quantum group is. It's this type of thing. Okay, so let's do a little bit more. So what did I just tell you? I told you that every sort of punchline so far was that every quantum space, which remember is just by definition a sigma model with boundary condition, has a fundamental group weight. It might not be an actual groupoid, it might be some algebraic version of it. Just like spec of a ring might not be an actual space, but some like algebra geometric nonsense. So we can do a little bit better than that. So let me do a little bit better than that. So what our project was actually about is about the higher homotopy groups. Let me sort of start telling you about higher homotopy groups. So we'll
Can I ask a question?
yes.
I just want to make sure, is there an actual example where you can tell me what the definition of spec, in this example, is there an alternative definition to spec that recovers that groupoid?
I should have said, I mean, yes. So what is the spectrum of a ring? It's just the representable sheaf, like the representable sheaf represented by that ring in, I don't know, the opposite category, it's a commutative rings.
I see.
And so the definition of this is you take the representable sheaf represented by this ring. Of course, that's not a groupoid, it's like does a type check. But I can pull a groupoid out of it by evaluating. And if I had a commutative C algebra, and I looked at its spectrum, that's some scheme. But if I wanted an actual space, I could evaluate that scheme on the complex numbers. And that's like the corresponding variety to the scheme. So I'll do the same thing here. I'll take my scheme and I will evaluate it on the complex numbers. But actually, I won't evaluate it on the complex numbers. I'll evaluate it on the correct thing in categories that corresponds to the complex numbers, which is I will evaluate it on the category of supervector spaces. And the category of supervector spaces is sort of the algebraic closure of Vec. The same with the complex numbers, the algebraic closure of Phi.
Thank you.
And if you're over some field that's of positive characteristic, then you need to work a little bit more, but there's a sort of story that's in development. And then this is literally correct. And now it's a theorem of deletes.
Thank you.
So let me talk about higher homotopy groups. So I want to make an aside about higher homotopy groups. The main aside about higher, they're going to be the same aside. So the aside about higher homotopy groups is that they're like a space doesn't have a pi2. Or rather, there is not a group called pi2 of a space. This is just not a thing that parses because pi2 requires you pick a base pair. And everybody knows this and most people ignore it. So let me just sort of remind you that what something like pi2 or pi3 or so on are, is they're not groups until you pick the base pair. They're groups that depend locally on the choice of base pair. So what is pi k? So if X is a space, so let me remind you that pi k of a space is not a group, it's not an element of abelian groups until you pick a base point. But rather, it's something that to any base point assigns an element. So it's a functor from the space of base points to the category of abelian groups. And while a priori it lives sort of locally on X, but this is just the one category, so factors to the fun number. So it's a representation of pi1, and I almost have the representations of pi1. So I'm like really in a good space to think about what this groupoid is. I'm a little bit off. And the reason I'm a little bit off is because these were representations, maybe I'm sort of implicitly talking. What's your favorite field? Okay, so maybe this was like I was working over the complex numbers and I was talking about the complex representations. And so I need to sort of get into the world. So I have really good access right now already to the complex representations of my fundamental groupoid. I'm looking for an abelian group representation. Fundamental groupoid. But I have a favorite way of turning any abelian group into a complex vector space. It's just my favorite way of turning any set into a vector space. I just linearize it. I take a basis. So I have a favorite way of taking an abelian group to a complex vector space, which is to linearize. So you take a group, and maybe my favorite linearization is probably the functions. This was like functions on it. I'm talking about spectrum. So let's talk about the function algebra. So I can get off algebra. So I can take a group and map it to functions. And that's a nice way of encoding abelian groups inside of linear algebra, because again, I can get the group back just by taking the spectrum of the corresponding. Hopf is going to remember that. So I'm already anticipating what I'm going to tell you in a moment is how to get a Hopf algebra called pi k, or rather called it functions. So let me sort of show the picture. So the picture is the following. So here's fundamental group void. It linearized, but before linearizing, this was just a disk, and I just had a kind of field on it, but it was just a disk, so that was just a point. And what do I want to do if I want to talk about, so what would I really want for just pi k? So if I was just doing homotopy theory, if I wanted pi k at a base point, what I would do is I'd pick some base point. So pick some point. If I wanted, so this is sort of how to build, so what is, who is pi k of x? I'd pick some base point, and I would set the field to have that base point. And I would look at some sphere, some k sphere, with base point, and I'd look at all the fields on the k sphere, all the sort of xy fields with that boundary condition. But my field theory isn't allowed to evaluate, and then I would sort of try to get a vector space out of this. Like, this is the space I want, the actual group I want is all the, like, my actual fundamental group is all this, the fields on a k sphere that have a prescribed value. And then I'll need to make this value vary, of course, if I want this functor. But if I pick a base point, this is the type of thing I want. That's sort of, if I tried to linearize a k manifold, I'll get some sort of like n minus k category, and I don't know what those are. So I don't want to do that. So let me try to linearize it just to a vector space, because that's what I'm after. But I can do that really well. I can just sort of thicken my sphere. So what I'll do is I'll thicken this up. So the dimension that'll give me a vector space. Now it's a solid torus. And over in one region, I'll just sort of thicken this up to n minus one disk, n minus two disks on the minus one disk on the boundary.
The reason you don't get a cross section, you have a patch and not a cross section.
Doesn't matter for this, but this is the correct answer for what we're going to code. So for this particular example, you don't see the reason, but it has to do with because of the fact that I'm going to want to be compatible with this pair of chaps. And so I need to be something that can patch on, live over a pair of chaps. And so that means I need to put the disk on the boundary and not in the middle.
That also specifies the framing. Because the chaps is only in algebra if you have a particular framing.
That's right, the chaps, because I said chaps and not co-chaps, it was framed in the sort of chaps way and not the co-chaps way. There is a pair of co-chaps, but it's framed, it's like the inside out chaps.
The compatibility with that determines the framing on this.
Yeah, that's right. That's right. And so if you think that through and look at this field configuration, then what have I done? Well, what have I just drawn for you? So I've just drawn for you a boardism. I've just drawn for you a boardism from the empty set to this disk. This boardism with boundary. And if you evaluate this boardism and ask what is the local system it assigns, well, for any point for any value of the field, this was just what this was just about the sort of pi 1 of x. For any point in pi 1 of x, the boardism works out to be the space of all field, like the linearization of the space of fields with that boundary. And so this boardism exactly selects in the sigma model case, at least in the sigma model case, this boardism does indeed select the vector space called functions on a pi k of x as an element in representations.
I don't quite understand how you're using the word boardism. So I would see this picture and go like, hey, that's a boardism relative boundary between the yellow part and the green part. Why do you ignore the yellow part? Or
so this is a boardism with boundary, and I've decided to put the green, the interior of the green is the outgoing boundary, and the yellow is just sort of closed boundary. So see, with boardisms with boundary, the right way to think about boardisms with boundaries, there's sort of two types of boundary. They have like sort of the closed boundary that's sort of been all lacquered and like glue doesn't stick to it. And then there's the sort of open boundary that you haven't put any finish on yet, where you can still glue other pieces of wood to it. And so there's sort of like, it still has the open pores to sort of glue it. So this is where the sort of the wood is still available to glue on, but then all of the yellow has like, is lacquered.
those two types of boundary have a physical terminology associated to
I have
them?
no idea. I've heard them called things like open and closed, but I think that's a terrible name. But No, I would call them lacquered and raw. So I decided to lacquer all the yellow boundary and leave the green boundary as a glue surface. And that way it's a border with boundary. I mean, I guess technically, if I'm really being consistent with my convention, then somehow the boundary of this disk is also lacquered. But it's the lacquered is one-dimensional. So the boundary of this bordism is torus minus a point. And then the bordism itself is like a jelly donut with a bite taken out. It's sort of the jelly can come out. Switched analogies. So yeah, so anyway, so the statement is that in the sigma model case, this bordism does indeed select. This is just a computation you can do. And you can work out that moreover, for some reason I lost, I do have a little bit of weight shock. Moreover, what you find out is that that if you take, let's see if I can get this correct. So if you take SK times the chaps of dimension n minus k plus 1, this gives you the multiplication on the group algebra. I told you it was a Hopf algebra, it should have a multiplication. And moreover, if you take the copants of dimension k plus 1 and multiply it by n minus k, this gives you the co-multiplication. And so you really do see the full Hopf algebra structure. And as I said, this is just a computation that you can do in this example. And now we'll tell you our first main theorem. Our theorem is that this is always true, that for any sigma model, sorry, not any sigma model, for any TQFT, the boundary condition, as long as it's sort of, it can be a really crappy one. I just need these manifolds to compile. As long as my TFT can compile on like chaps and jelly donuts, then the theorem holds. It doesn't have to be extended. It doesn't have to be compact. It can be as co-framed as you want it to be. So for any TQFT with boundary condition, the bitten donut, the bitten jelly donut.
To be fair, a jelly donut doesn't usually have topology, right?
But I mean,
You'd have to take a standard donut and fill it with jelly through the middle. I'm just being fussy here. But
so I eat very few donuts. Like I don't know, like Tim Hortons is just sort of not part of my
I'm a lifelong jelly donut.
I apologize. I'm sorry. Whatever. Yeah, so the bitten, was it actually called? It was actually called SK times dn minus k. Is a Hopf algebra in this category, this n minus k disk category. I mean, this is a statement like in the bordism category. This is a Hopf algebra object in the space of bordisms from the empty set to this disk. That's our theorem. Yes. Is the antipode?
Yeah.
No, it's not clear at all. No, but it's really, really cool. So the question is, what is the antipode? Which is a great question. And the answer is the following. I wasn't going to say this, which is I'm really glad I'm in shock because it wouldn't be on the slides. So the answer is the following. So there's, forget about the bite for a moment. That takes a little bit more work. But if I just wanted to do this on sort of this the unbitten, the pristine donut, then what you could do is there's an antipodal map on this K sphere. which does like crap with, I mean, this might even not preserving orientation, something's gonna mess up the framing. And there's an antipodal map on this disk, same thing, it may mess up all sorts of things. And what you can do is you can do the antipodal map on both the sphere and the disk. And then there's, so that's some diffeomorphism of this donut. And then you can cleverly unrotate the framings back to being a frame diffeomorphism. So there is a frame diffeomorphism that lives over the sort of twice antipodal map. And sorry, I lied to you. I totally lied to you just now. Because you should have already complained if n was odd, what I said could not have been true. Let me try it again. Take a single reflection in one of these dimensions. So where you just like pick one of the reflections on this case, and pick one of the reflections on this disk. So now that's two reflections in R2. And now sort of unrotate those two reflections just in that plane. You might need like 1/3 dimension to do this. And that's a frame diffeomorphism of this solid donut, and that's the. So if you really like sort of random slogans, that's like the way I sort of for a while was thinking like one of these was called time and the other was called space, and so this was like and then he puts like charge conjugations. It's like a CRT statement. So a priori you do. If you're in really, really low dimension, then it depends on which of the two rotations I did, and you would get both. But most of the time, this thing is at least one of commutative or co-commutative. And so it's.
So this works for K for 1, 2, and 2.
Yeah, that's right. There's some range on case.
And you get these and you pop out of they are they related to each other in some way?
Are the different homotopy groups of the space related in some way?
Always.
I mean, the answer is, of course, the different homotopy groups have like connective tissue called like Postnikov classes. I have no idea how to see that in this story. We're still like a sort of a future me or future you or something. Like I don't know how to see the Postnikov data.
So Theo, maybe you said it, but it should have the x of the n minus 1. The value of the TQ of t on.
Yeah, sorry.
I thought your original theorem was in the carbonyl category itself.
Yeah, I mean it is like okay. So maybe X is the identity functor from the Bordism category to itself. So this is like the universal TF2. And indeed, we prove this in the Bordism category. So I have how many minutes? I have like 12 minutes or something. So there were sort of two things I wanted to tell you how, or sort of two things I wanted to tell you. One was that this theorem is actually follows from in some ways that even more important theorem. I mean, this I think is really cool. But let me sort of tell you how we prove it. So although my TFT might not be extended, my Bordism category itself is. Because if I want to prove something about manifolds in a Bordism category, I'm allowed to do computations in an extended Bordism. As long as at the end of the day, I'm just proving something that parses in an unextended Bordism. Because like the unextended Bordism category fully embeds the extended Bordism. So I'm allowed to prove this in the Bordism category by going down a few dimensions. And what we do is we sort of start slicing this up. So I could say like, why would, okay, so for instance, you could ask the following question. You could ask like, why is the chaps an associative algebra? Like what really makes chaps associative? What really makes the copairs co-associative? And the answer is that the reason chaps is associative is that the chaps themselves, the disk itself, is an endomorphism algebra. So the disk itself can be sliced in half. And now it's a Bordism from nothing to a disk 1 dimension lower. And the full disk is the endomorphisms of that half disk. And the reason why the chaps is associative is just from that monadicity. And so what we really do, sort of the way we prove this is we start slicing this manifold to a couple lower dimensions and getting another down two things. And I'm sort of running out of time as I'm trying to decide which things to tell you. So in general, what we do is we have the following more general theorem. So the proof idea is sort of you slice up and then use. Is slice your donut into slices. Slice the donut down the middle. And use the following theorem, which is probably useful for other people for other reasons. Well, I'll just state this theorem. I won't tell you anything about why it's true. I'll just sort of state it. And I won't even state it sufficiently precisely, but here's the theorem, is that if you have any retract, I'll show you the retract I'm going to apply it to, but here's the theorem, is that given a retract, so what's a retract? That's just I've run out of letters already. Retract, so a P and a Q and a map down and a map up such that that composition is isomorphic to the identity. So suppose I give you a retract in three category, infinity three category with all duals. We can say a little bit more. I don't really need all duals, but I need some duals, so all is enough. So given a retract of three category with all duals, we get a Hopf algebra. And the sort of part, the really fun part was actually that it's Hopf and not just a bi-algebra. We get a Hopf algebra in so you can take the endomorphisms of the downstairs object. You can take the identity on the downstairs object, and you can take the endomorphisms in the of the identity objects. It's like a twice endomorphism. So this guy's this is some E2 monoidal infinity one category. So actually, I can sort of produce a lot of Hopf algebras in infinity one categories this way, and like.
Upper left end.
Sorry, this is like end of this thing. It's just endomorphisms of the identity. It's just like the twice endomorphisms of Q. It's like the two endomorphisms of Q. And then three categories. Yeah, sorry. Anyway, this is like you could write this like n squared of Q.
Do you mean in whole of that? Like I
No,
don't know.
no, we actually get it at the coherent level.
I see. What's an E2 Hopf algebra?
It's in. This is just a Hopf algebra.
So it's an E1.
It's an E1 and co-E1 algebra with the property that the shear map is invertible. In this E2 monoidal category. And I need the category to be E2 to talk about E1 co-E1.
I see. Okay.
So this is some E2 category. This is some E1 co-E1 object in this E2 category and has the property that the shear map is invertible. So that's our theorem. So the retract, let me see if I can actually, yeah, so the retract we use it, still lots of time, this is great. So the retract we use it for is the following, is the following retract. I'm actually looking at my note cheat sheet for this because I probably remember it, but so I thought I needed to slice this up. So I sort of. So let me slice my donut in two different. So this donut has two different slices. I can sort of slice it sort of this way, and now that slicing kind of looks like that as sort of its cross section, and there's sort of a handle and a handle. And there's another slicing which is to sort of slice it sort of front and back. So if you do those two different slicings and look at sort of say the sort of. So what you can do is you can draw this over here. You can take kind of here's half of a slicing. We have sort of put in red the sort of regions where I'm slicing. So red is where like my knife has gone through the donut, like in sort of codimension 2. So there's one way to sort of, so what I did was I sort of sliced it sort of vertically on my picture over there, just took the cross section, so just took that boundary condition and like threw away half of it. So this is a bordism from something to something. And then I could, so this is a bordism from, I think I want to read this. This is a bordism from maybe nothing to something. Anyway, the middle space that I'm gluing over is this kind of pair of things, sort of orange boundaries, and I totally where's my white chalk. So sort of starts at something like, so there's a bordism, and then there's another bordism from here to somewhere else, which is where I sort of slice them the other way. I can sort of take the horizontal slice first and then throw away half of it. That looks like sort of a horizontal slice, so maybe I don't know which direction. And this is a section retraction here. Composition here is just a sort of disk with green and orange, and so I forget what source and target I wanted, but this is a map from sort of an interval to interval. It's like a map from the green disk to the. There's my section retraction. And if you apply this theorem to that retraction, I have 5 minutes left, which is awesome. So. And this is not intelligible at all. This is just me recording it for the video, so that in a year when I'm going to write the paper, I can be like. I'm going to tell you one other theorem that we have. So homotopy groups are great, but they're not the sort of best thing in the world because it's like, you know, it's hard to compute them. I mean, it's like hard to like one homotopy group is not very useful, but like lots of homotopy groups are great. And what I mean by that in particular is that one of the only facts I know about homotopy groups is that they fit into long exact sequences sometimes. So run out of time, which is fantastic. I won't have to actually write formulas down. I'm also out of white chalk. If you have, so let me remind that if you have a map of spaces, if you have a map of spaces, it might as well be a fibration if you're, because I'm just doing homotopy theory, and then has some fiber. And the fiber is, of course, not really a fiber, it depends on a base point, but a fiber of the space is like a local system on one. I mean, it's just that local system is the straightening. And at least if you sort of fix a base point, then you get a long exact sequence of the Pupa sequence. A long exact sequence. And what it tells you is it tells you that the homotopy groups, you get a long exact sequence that goes like the homotopy group of the fiber, the homotopy group of the total space, the homotopy group of the base, to the homotopy group of the fiber. And if you want to do this without picking a base point, this long exact sequence lives in local systems. Is that local sort of functors from pi 1 of x? So if you want to pick a base point on f, f already dependent on a choice of base point on y, and then if I want a base point on f, that combines to a base point on x. And so this is really why it's sort of everything is sort of living over x. So that's the Pupa sequence. And so what should I think of map of spaces? Well, I started out by telling you a bit about boundary conditions, and if I have a map from x to y, I can get so given, I should have given these colors. Let's say I have a space x and a space y. then what I can build, one way to encode a map of spaces in terms of sigma models is, remember, I want to encode a sigma model as a sort of, it's sigma model with Neumann boundary condition. So I can sort of think of this as like, I can encode this as a sort of the Y sigma model. And it has some boundary condition, the Neumann boundary condition for Y, which is maybe the sigma model for Y with its Neumann boundary condition. But there's another boundary condition I could use, which is to say I could talk about fields that take value in X along the boundary. So fields with a lift to X. So that's some other one. It has a stupid name. It's called mixed Neumann-Dirichlet of X. That's just its name. Sorry. But anyway, you know what it is. It's the boundary condition of the field takes value as X. And these two boundary conditions meet at a corner that I don't think doesn't have a name. I just sort of do extend this. So this is really kind of like like the sigma model on X. So any map like this I can code as a TFT with two boundaries in the corner. And I want to tell you that just like I think that a TFT with a boundary condition should be thought of as a space, I'm going to tell you a TFT with two boundary conditions in a corner should be thought of as a fiber bundle. And so this is what a prototypical, what a sort of quantum fiber bundle is. A quantum map, a quantum map of spaces. Picture like this. I want to warn that this is not symmetric. So if I have a sigma model, if I have a TFT with two boundary conditions in a corner, there's another TFT with two boundary conditions in a corner where I switch the roles, and the answers I'm going to get are going to be different depending on those two interpretations. And I haven't really explored that. And our theorem in the last, I started at like 2 after or something, and I have 2 more minutes. So our theorem is the following. So let me point out, for instance, that you can already extract Y from this just by ignoring half the boundary. You can extract X from it by collapsing it down. So you already see two spaces. So any map of space, anything like this has 2 spaces in it. One is sort of just a sort of, which is this picture, and the other which is just folding it in half. The fiber is a more complicated thing. I won't tell you how to do that, but our theorem is that given a TFT with 2 boundary conditions in a corner, we get, there's 2 things. We get a long sequence of Hopf algebras. A long sequence is just a long exact sequence without exactness. Meaning that it's like literally a chain complex. So you get a chain complex of Hopf algebras. And it's usually exact. And it is exact, exact, sufficient conditions for exact. I don't actually know any example where it's not exact. Well, I think it's not exact in the Bordism category itself, but then I don't really know what exact means. So I'll say a moment what I mean by this, but it certainly is exact in the following case. It is exact, the sufficient conditions for exactness are it's exact if all the Hopf algebras in question, all the Hopf algebras in question. I mean, and I should say, like, you get a long sequence of Hopf algebras and it recovers the Puka sequence. In the sigma model. And it's exact at least if all the Hopf algebras in question are separable and co-separable. And maybe I'm making the organizers annoyed at me by continuing on. So let me sort of tell you a moment what sort of a Hopf algebra being separable and co-separable is. A Hopf algebra is separable and co-separable. This happens if and only if just a general fact. It's a fun exercise. So in any you can prove this in any braided monoidal category, maybe in any crudely complete braided monoidal category. But like crudely completeness is something you can always assume because it never hurts you. At least I don't even remember if you need crudely completeness. What I'm going to say. Essentially, in any braided monoidal category, if you have a dualizable Hopf algebra, so Hopf algebra's underlying object is dualizable, then it's separable and co-separable. This happens if and only if what you can do is you can take the antipode. Say this happens. This is if and only if you take the antipode and you square it. Now that's usually the identity because usually it's commutative, but it's not always the identity if you're sort of weird. And you take the sort of eta trace. So you take the sort of trace around a circle with that circle. Take this trace of the square of the anticode. And you ask this to be invertible. This is some endomorphism of the identity object. It might not be invertible, but if it is invertible, this is just a sort of cute fact that I don't know. It's sort of the type of fact that they should have written down in the 1990s. Maybe they did write it down in the 1990s and I haven't found it, but like. So anyway, the way this works is that like once it's invertible, then I can write down some idempotence that sort of I can use to sort of actually give an equational reason for exactness. Exactness is a really, really funny thing from the perspective of TFTs because the whole point of exact sequences, they're not preserved under functors. But all TFTs can do is they can apply functors to things. So I always need equational reasons for exactness. And this is enough to give me equational reasons. So I think I will stop here. Oh, and I won't stop, I'm sorry. Let me just make one last comment, which is to say, as I said, this is about separable and co-separable. And these Hopf algebras just arise as endomorphism algebras of things. They're just values of TFTs on things. And so most of the time, most of you probably think about TFTs valued in things like 2-vec or algebras or categories or something like that, somewhere where separability happens all the time for finiteness reasons. So most of you have this condition in your daily life. So this is a fairly mild condition for most of you. If you really like non-semi-simple things, then that's where you would have to worry. So now I stop. Thank you.
Question. Sorry.
In the case that k equals 1 and n equals 3 at least.
Yeah.
Like there's just a solid torus the usual one. And I'm wondering if like the fact that you should be looking at modular tensor categories can kind of be directly read off from that picture and act upon it.
It's absolutely, so this is a great question. So the place that our project started with, like we started in a really different place. And where we started was really trying to understand this, the non-degeneracy of the S matrix. And really trying to figure out like what was going on, why should the S matrix be non-degenerate? And what we eventually understood was the following. So we eventually understood, so the statement should be the following. You take the Notre theory and you look at its bulk. And the statement is, which is a sort of statement, I mean, you can just like find this in, I don't know, Jordan, Safranov, Snyder, or somebody that I'm forgetting and I'm embarrassed by as soon as they see the video. The statement is that the bulk is invertible if and only if the S matrix in the boundary is not degenerate. And so we were trying to kind of give a different reason for that. And like in the case of sort of Notre and Levin-Wen models where you're fully extended, we can just sort of, you can prove that pretty directly by using a theorem of Chris's. But we wanted a sort of proof that that was very, very agnostic about TFTs, didn't require any sort of hardly any extendability, didn't require that I know about fusion higher categories, that kind of stuff. And so what we eventually got to was this point, and we sort of started noticing these long exact sequences. And versions of this long exact sequence, I should say, so some version of this long exact sequence were very motivated by the initials are FSV, and I can't remember the people who is attached to it. But there are sort of some, in examples in low dimensions, versions of this long exact sequence were already observed. And so we sort of had good guidance to where to look. So, so then eventually sort of started saying, oh, there seems to be this long exact sequence. It was sort of reminiscent of a Pupa sequence. And then we sort of started to be like, okay, is it a Pupa sequence? Like what's going on? So yeah, so that's what I can say. No idea, but that's something to talk about in sort of longer form.
Questions? Computers, please.
Talking about Notre, like didn't they have a paper on this in the 90s about, but obviously in the 3D case or something with it that they like
the once-punctured torus is a Hopf algebra object in the cobordism.
That's right. So there are a bunch of papers of that form about like finding Hopf algebras in like specifically 3 and 4 dimensions. And so from that perspective, what we did was we did we're fully every dimension. And although most of my story was about sort of saying, oh, I hate higher categories, of course, this is fully coherent. Really a Hopf algebra in the true bordism category. Sort of all coherence you want. And this is useful, for instance, so for example, Tudor de Mofta has explained how they got a whole lot of quantum groups, just like actual quantum groups, like the ones that drink, that like real quantum group theorists like. Sort of not from he doesn't care about this stuff, but from this theorem. I didn't tell you why this theorem, like I didn't sort of show you what was really going on in this theorem, but what did I tell you? I have a retract pair. Okay, let's talk about this theorem one. Suppose Q is just say like the vacuum theory or VEC or something like that. And suppose P is some other TFT. Then these two maps are sort of boundary conditions for P. And the fact that it's a retract pair is that those boundary conditions annihilate each other. So that's a transversality condition. Those two conditions. Or maybe you think this is some like fusion, some monoidal higher category, some monoidal category, and this is VEC, and this is like the unit inclusion on a fiber function. And so for various versions of this, so the one that Tudor wants is that this is some TFT, this is just the vacuum, and these are two boundary conditions, and the retraction is that they meet transversely. And then I'm telling you that anytime you have that data, you get a quantum group, you get a Hopf algebra. And depending on which dimension it is, depends on the dimension. And what Tudor's explained is that basically every quantum group that you've ever met comes from this construction in a sort of physics way. Like there's an actual physical theory with two boundary conditions that you apply this theorem to. So. And also I was saying like Tanaka duality comes this way. If you take like, if this is some sort of higher category and one of these is sort of a fiber function and the other is like a unit inclusion or something like that, then you can get the, then you can run this machine and get the sort of Hopf algebra that corresponds to sort of the model higher category.
When the unit happens to be K.
Yeah, that's right.
So maybe we'll postpone other questions, so that just in case people want time to get back to their hotel room before they make it to the bus, we have that time. So let's thank Theo.
It sounds like we should also